round 4 is very similar when we're talking about the difference between speed and velocity, as we talked about the difference between displacement and distance, right? So speed and velocity, close cousins, just like distance and displacement. Their differences are similar, right, as what we just went through with distance and displacement. So speed is what we would call a scalar, just a number, right? Does not care about direction. Again, it's what you see on your speedometer. How fast are you going? You're either going 70 miles north on I-35, that would be a distance. You're either going 70 miles per hour north on I-75, that would be like a velocity. But if you're just going 70 miles per hour, that's all it says on your speedometer, 70 miles per hour. Whether you're going north or south, that is your speed, right? It doesn't say you're going negative, right? That would be velocity. So velocity is a vector. It's a number that we call magnitude, and we also specify the direction, positive or negative. It's what we call the direction of that arrow we've been drawing on our pictures. So speed is how fast a person is changing distance in time. We call that a rate of change. The rate of change of distance, how fast you change distance per unit time, we call that speed. Makes sense, right? Speed is a scalar, distance is a scalar. So if you take distance divided by time, you get a scalar, which is speed. Velocity is how fast a person is changing displacement over time. So it's the rate of change of displacement, that straight line distance that has a direction associated with it. Also makes sense. Displacement is a vector, velocity is a vector. So those two things kind of match up. So I have it written in terms of words here. Also have it written in terms of symbols, right? Speed, right now I'm calling S, and then distance calling D. You may see that different in different books or notes that you look at, right? Velocity is delta x over delta t, right? So that delta x is x2 minus x1, delta t, t2 minus t1. Other ways you might see in terms of vector notation, you'll see a little bar above the x and a bar above the v, or they might be a boldface, right? But it's really important that these equations, they start to speak to you in terms of answering a question, right? For this velocity question is saying, if I were to walk from x1 to x2, right? If I were to walk from x1 to x2 in some sort of amount of time, so there's my delta x, what is that constant velocity I would have to walk at to make the trip in that amount of time, right? This is assuming, right? I'll write this out. This assumes constant velocity. It assumes your velocity is not changing between x1 and x2. That's an important distinction. It's a fundamental equation, but it assumes that between these two locations, x1 and x2, you're moving at a constant velocity. And as we'll find out, I think in activity, linear motion with acceleration, right, where you're changing your motion, that velocity assumption of being constant is sometimes good and sometimes not good, right? But that's what these equations are speaking to us. That's what they're telling us. So a couple of problems here, and boy, it looks familiar, but what we're doing here is we're a person from Boulder driving to Denver. Takes an hour. You stay in Denver an hour. You go back to Boulder in 30 minutes. And it wants to know what's the average speed of the round trip. Now, before you give this a try, right, I just want to remind you, right, speed is distance over time, right? And the distance that we had from up above was 100 kilometers. All right, so we'll give it a try. I'm looking for my calculator here, but you should be getting to that right answer. So if distance is 100 kilometers, what do you use for time? What do you use for time on this one? That's the thing that kind of gets people, right? Well, you have the right answer, so now you should know what you're using for time. But if you start at the start and finish, right, all you're doing is you have one person at the start, one person at the finish, and they synchronize their clocks, synchronize their watches. They push start at the same time. They push end at the same time, right? Or you start and you finish. Just because you stop and you're not traveling does not mean that that timer stops, right? The best example I like to give in class is if you run a marathon, right? When you have to tie your shoe because you didn't tie your shoes well enough, you stop, right? Do they stop your timer for you? Do they? No, no, they don't, right? That timer keeps on going. You have to use the restroom. That timer's not stopping. You gotta stop and get a drink of water. That timer is not stopping, right? So you run 100 kilometers in that certain amount of time. This says if you were to make the whole trip, right? If you make the whole trip in, what would that be? 2.5 hours. So you take 100 divided by 2.5 and you get 40 kilometers per hour, right? If I made this trip and I never stopped, and I was always moving at the same speed, a constant speed, what would I have to walk at? I'd have to walk at or drive at 40 kilometers per hour. It means you couldn't wait in Denver for an hour to talk to your buddies. It means that but it also means you wouldn't have to speed home either if you're going twice as fast, right? Half an hour, right? So that time here is 2.5 hours. Divide those, 40 kilometers per hour. All right, how about the next one? Person starts in Boulder, drives 50 kilometers, stays an hour. Denver, 1 hour, speeds back in 30 minutes. What's the average velocity for the trip? Give it a try. So I want to get that average velocity. It's your delta x over delta t. You may recall that displacement for the round trip is 0. Right? 0. 0 divided by whatever is still 0, but I'll still put in 2.5 hours, but you still get 0, right? Your average velocity is 0, right? It's like if we did this, right? Here I am, Dr. Ray's been sitting in this chair. You've been sitting in your chair for a while, right? And so you start the timer, right? I stand up, right? If you closed your eyes right now, I should have done that, right? I come back, there I am. Right? Had you closed your eyes, right, and I got up, walked away, came back, you would have no idea that I did that. If you closed your eyes and then you open them up and I just sat right here, you'd think, oh, Dr. Ray hasn't moved. His average velocity is 0. When in reality, I actually did move. I actually did. So the answer to this one, well, you have it, but it's none of these guys, right? 0 is not an answer choice. Okay. This one, not going to run through this one with y'all, but I'll get you started on this, right? You have a marathon runner. That's the big smiley face, running at a steady 15 kilometers per hour. When the runner's 7.5 kilometers from the finish, a bird, that's the little circle there, is flying from the runner to the finish line, right? Going just boom, 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 right back, right? But as this runner's going, right, the bird doesn't have to flies back and far as much to go from the finish line back to the person. Okay? So when it reaches the finish line, it turns back, flies back to the runner, gets back, runs, go back to the finish line, keeps repeating back and forth, back and forth. And the question is how many kilometers did the bird travel? Right? Now you're going to solve this. You're going to solve this with 2 equations. One is going to be for the bird, and one is going to be for the runner. And it's going to be the same equation for both, right? But it's going to be for different people, right? Those equations we have in this round, right? We have, well, let's see. I think it's going to be using speed here. We're going to be using speed instead of velocity, right? So speed of the runner is equal to, whatever distance the runner is going to go divided by however long it took the runner to do so, right? And then for the bird, you have the speed of the bird. It's going to be equal to the distance of the bird, right, divided by the time of the bird. Okay, now what you have to think about this is, what are you trying to solve for? Well, should hopefully know what that one is. That's the distance the bird traveled, right? Which means you need to know things such as speed of the bird, which you do know. But what you don't know is that time that the bird was in flight. That's the guy you need to solve for. And at this point, give it a try. And before I jump forward too much, Yeah, okay, next round. Haha, don't want to jump the gun again too early. Have fun with this one, guys.